very much indeed for inviting me, and today, as I want to explain to you, we'll look at mathematical billiard systems. So the idea why I want to present it is go somewhat beyond the idea of billiard systems, because I want to present a task which can be varied through a number of grades at school and at the university. And I want to show some students' productions, showing how they experiment, how they give conjectures, and how they try to make proofs. And then I would like to show you a small study which wants to find out whether experiments can stimulate mathematical arguments, proofs, and deep mathematical knowledge, because this is, at the end of the day, what we want to do in mathematics. And later I would like to discuss with you whether it's possible to extend it perhaps to other questions. So what is the situation of the teaching and learning at schools today? It's probably a bit German-based, but from what I heard in the last day, maybe a bit similar to the situation here. So we are experiencing a lot of time pressure at school, especially in subjects like mathematics, which define themselves according to the curriculum. So the curriculum is built up gradually, and we have to rely on what has been done before to advance. This pushes us in mathematics more under pressure than, for instance, in literature, where it's not that much of a problem if you leave out one novel or another. If you have standardized exams, this puts a lot of time pressure on you, or if you have entry exams for the universities, because the students expect you and the parents expect you to make your students fit for it. So the trouble is there actually any time to incorporate mathematical activities anymore, such as problem solving, conjecturing, defining, hypothesizing? So you have all the recipes which you need to know to be good in exams. It's still possible to give actually a feel what real mathematics is about. So one contribution to this challenge is perhaps to vary the same task over the years. So the problem is, if you introduce a complex situation, this takes time of your lessons, and you don't have time. So it's good if you have tasks which are easy to approach and actually which give you, right after a couple of minutes, everybody the idea of what is going on. And in the following, I want to discuss the following task with you. Choose a billiard game on a table of a circle chain, quadratic, rectangular, circular, so what you like. Assume that the table has no holes and that the ball moves at constant speed. Can you describe its trajectory? So I gave this task in my experience as school teacher and at the university to several grades. Here my school experience, so 4 years I was in school, so to the grades 5, 7, 11 and 12. And I had students in certain extracurricular classes from grade 9 on, and students in the first years at the university. And I want to invite you to have a look at what the students did with this task. Let's start with grade 5 in the Gymnasium. That's the German way of the highest level of school education you can have in grade 5. Look at the solution of Celine. You see, perhaps it's, well, not that easy to spot, but you see a circle and you see 3 points and you see, now the question is, what has she done? She writes, I just gave it a try. Staring, ball, Francie's earring, that's my maker, cue, my pen, wall, my sharpener. I put the wall at the point where the ball should hit it. Then I put the earring next to the point where the ball should start. Then I shot the earring against the wall. And so what she writes is somehow, I think, a kind of, or summary, an average of the experiments she carried out. Well, the question you ask yourselves perhaps is this mathematics? Well, you know that this is mathematics here, or physics, so you have the law of reflection on a cushion, so you have a ball, it comes, and then it goes away. But at least what she might have observed is something which is more implicit and hasn't been in our classes before. So this is what happens actually in the case of a circle. So how do you find the law of reflection for the circle? And if you talk to them afterwards, you see that this was her motivation to carry out the this example. So what happens when you have other obstacles where you reflect? So somehow, well, she goes from outside because her sharpener was round from the outside, but look now at the inside. So you see that it comes to somewhere, and then you have here somewhere a tangent, perhaps, as the best linear approximation, and then it goes on. Of course, she didn't write this, but we took this then, her construction, as an idea to discuss this and to try to define how reflection is done with different shapes. The question is how to catch these ideas, so there's a lot of going on when you read something of experiments that you carry out in mathematics. The trouble is how to catch these ideas and moreover how to hold to it. Especially in stochastics, for instance, if you carry out exam, you can do a lot of experiments, but unless you take notice of them and you work with them systematically, I mean, it just goes away. It's somehow wasted time, yeah, if you don't do anything with it. So what I do is that I force them to write in a traveling diary. This means that you have structured tasks where you document experiments, thoughts, and problems. And this gives an individual feedback, first from the student to me to see what they have done, also in terms of reliability, that they have to show that they have done something. And of course then from me to the student to say how to go on and what to do. Of course there are different approaches to it. I prefer problem-solving based, experiment-based tasks for it, because otherwise it's very hard to correct it or to give advice what to do. So my feedback is normally an oral one. Let's look at the following solution by Batu, the same class in grade 5. You see here some other constructions which are going on. So he doesn't write anything, that's not the way it should be done, but at least he tries to indicate with arrows what has to be done with it and how this should be understood. Well, the question is what you do with this. Let's look at another solution, same class of Henry. Henry's a very smart guy because, well, you have perhaps an idea what he did and then look at what he writes. I have drawn a circle with radius 5 centimeters. I then selected 2 points and set the radius to their distance. Then I have drawn the quarter of a circle around these points. At the end points, small b and small d aligned to capital A and capital C. Well, whatever what he does there, it is probably not quite honest, because the radius, the distance between the points, is the same as the radius of the circle. So I asked him whether he cheated a bit, and he admitted, well, yes, well, while writing up, I found out that actually, well, what I did was not quite the general thing. Well, if you give him the table, you want to have, well, somehow a general description. So he found out that somehow it must be more general. Then we discussed why his example is pretty special, and we found out the regular polygon with 6 edges. Let's have a look now at grade 11. We have the same task. Now there's a slight variation for one reason or another. Sometimes I just said, well, to light in a box, and the box has a mirror, and it has a certain shape of the same thing. Now, this is the solution by Nick. Nick is a very efficient student. He writes, I took a rectangle as a box shape and started at point P1, that's the top and the center of the line, from which the light beam passes to P2, that's on the right hand side upper. Then I set up a linear equation and consider the slope of line P2. Then I have computed the intersection with the line at x with the equation x equals -6, and so on. Later he writes, there are only two slopes, 1/2 and -1/2. Of course, we took this conjecture or observation as a reason to carry out a proof, which is of course not difficult, but for someone like him it was quite a development to be, well, first to see that there needs to have an argument. Yeah, you just cannot give just a conjecture like this without understanding why, and then we've seen that it is not that difficult to give an argument. It is also quite an important experience. So, another thing which you spot perhaps is, well, the students tend to apply the task to the context they are normally in. Yeah. So here we just, in preparing the analysis of one variable, we looked a bit at basic functions and linear equations which describe linear functions and so on, and you see that he just picked one of the examples which he could easily handle. But at the same time, it is just perhaps not directly for him something to do a conjecture, but something to experiment and to work, or just to have an exercise of what he does normally with lines. And this is fine. Why not doing an exercise in a framework which is perhaps a bit more interesting than task from A to B to Z, D, something like this. Another thing which is typical here, and you observe in many other situations, Henry's example was another one, is the preference for symmetries, if you observe what the students pick. So here this may be both convenience, perhaps a bit laziness or whatever, or just beauty, I don't know. But in any case, he likes to have symmetric solutions. So what is actually important about this task? Well, I don't think that this task is important because I think that every student needs to know how billiard ball moves. But I think it is rich because it's paradigmatic for a lot of activities in mathematics. And it is pretty rich because you can change the geometry easily, and then you get quick variations. Actually, most of them take classical billiard tables. This is good because if you change it, it gets horribly complicated. Yeah, so if you take the circle and you remove from 2 points a segment, you get already something which is so-called C-day billiard, so that's very complicated, and this pretty chaotic phenomena can be observed. So all these are examples of integral systems. I will show another 2 or 3 slides later on it. So, and the other thing which I like about these examples when I teach about it is that it's possible to distribute different activities, experimenting, conjecturing, proofs, according to the levels of the students, and still they all contribute to the same idea. This means, of course, for some it is undoable to give certain proofs, as shown later now. Some already harder proofs or harder conjectures. And then for some it's very difficult to do this, but others can do experiments and you can still discuss in the class by presenting what they've done that everyone participates, yeah? Even if it's easy for one of them and more difficult for others. I now show you an example. Now here the production which I show is from an extracurricular lesson, so it's in the afternoon for interested students. It's here from grade 10. And we asked ourselves the question, when does the ball of a ray return in a rectangular billiard? And the students here started from it with the problem of the edges. If you have a rectangular billiard, yeah, then the model which you have is sort of a problem, because you don't know really what happens if the ball directly hits the corner. So my answer was, well, just assume it doesn't. But of course this just attracted his attention even more, and he wanted to go through it. So his question was, when I start in an edge, when do I get back to it? And after experimenting a while on the stage, you see now here an idea that of course instead of doing the reflection of the ray, the student had the idea that you may reflect the tape. Yeah, I don't know, perhaps I show it for a moment. So normally here, this is somehow the trajectory of the ball here. And now if you reflect the table, instead of reflecting this here, you can just go on linearly like this. So this means afterwards a proof like this came out. So that you see here the numbers which refer to the picture on the upper left corner of the sketch. And you see now how these segments just continue as a line. And so it just means, you see here, that the ball returns if the line is rational. Because then it goes to the grid with a rational coefficient somehow. And if you have an irrational slope, you see it cannot return, because no natural multiple, no rational multiple will ever be an entire pair of antennas. This is of course, I think, difficult because you need a deeper understanding of rational and real numbers, and this is probably one of the toughest things you have in school mathematics. But still, if you have the rectangular base, billiard, I think it's fine if some of them just carry out the constructions or find out the slopes, calculate what the lines of movements are, and the others do some conjectures. You still have variation in the classroom, although they just participate on the same goal, namely to understand better what happens with rectangular billiard. Here's a different approach of someone who wants to show that he's already someone who has Polya's strained with Polya's ideas, I think. So he tried to do it differently. You see, he's a bit sloppy. He doesn't use a ruler and things like this. And he has picked a rectangular billiard where one slice is twice as long as the other, and he tries to compute somehow the length and wants to go to see whether it returns, and he has written down a condition. So due to the fact that he starts at the middle of so the first ball is somehow, of course, a constant which doesn't change, so it determines the parameters, the starting condition, the initial condition for the problem. And he says that modulo 2, this expression should equal 0. This is something he doesn't write, but this is what he means. So it must return means that somehow modulo 2, because the length is 2, it must return. He wasn't able to carry out the idea, but just to formulate it, to say what it is already something which is not so easy, but he wasn't then clear what to do about it, and we needed help then to make an argument out of this. But this is what teachers are good for. Here another example of Christoph in this class of grade 11. And he wanted absolutely, because this is partly was also part of something we did before, just in, repeating things which are useful for analysis. We did some polynomials of grade 2, so he wanted absolutely to see a rectangular, not a rectangular or something like this billiard, but one with the shape of a parabola. And then my idea was just quickly, because I thought, well, this gets very difficult. Otherwise, I said, well, just try to do parallels to the y-axis, because, you know, this is how the Olympic flame is inflamed, so this is a good idea. Just see what happens there. And then he spots here that they all go through the same point, as you know. So we are close to the classical definition of parabola, something which has, at least in Germany, vanished from school. So now I want to discuss this a little bit in the framework of the computer use, just to give you also a couple of ideas how to experiment perhaps yourself. So I did this in extracurricular activities from grade 9. So the question is, what happens on the long run with a circle? Probably you are not that surprised about this picture. And you see now already that if you have this, a lot of questions happen and come, which you may ask. So, is this actually periodic or not? If it's not periodic, does it come to every point arbitrarily close, arbitrarily open? And a question like this. Now I want to invite you, as a thinking experiment, to go to a slight variation of this. So it remains classical. So what happens with the elliptic billiard? So if we take here certain points, you see that something similar happens. And you get a feel that inside you have an ellipse to which every segment is tangential. And in fact you only, but this is an exaggeration because it's still pretty hard mathematics, but you need only elementary geometry of theorems of congruence to prove this. But it's not a proof of one line or so. It's really, it's a bit tough, but it's doable with students, probably with your help. Now I've got, so what you see here is it's always tangential to it, so physicists call this a constant of motion. Yeah, because whatever happens with the segments, they are all tangential to this. You can describe this with the equation of the ellipse. It's not whatever ellipse. This ellipse is confocal. This means it has the same foci, but with a smaller radius in the sense of that the sheep you get around, yeah, this gardening ellipse has less freedom of movement. So, okay, now what we did was we considered the segment which avoids the segment between the foci. Now I invite you to think for a moment what might happen if you just go through it. Of course, I mean, then it's not possible that it's always tangential to an ellipse with the same foci. Yeah? Because somehow it intersects it, obviously. I mean, if you take whatever ellipse which has these foci, it goes through it. So this doesn't work. So let's try to see what happens. So the first thing one sees if you carry out experiments is that it always then goes through the segment between the two foci. And then if you write it down, it means that if you continue like this with complex numbers and so, it remains the same equation. But you see that this is now, these are now hyperbola with the same foci. So if you go through them, then you have still a polynomial of grade 2, which describes the curve, but it's no hyperbola. Okay. Again, doable if you have the definition, the classical definition of a hyperbola, as the difference of the distances to the foci. This is constant. It's doable to prove this with congruence geometry, but it's of course tough. This goes back to a more historically, it's already pretty old. Even a generalization of this goes to Poncelet. So here you have all the possible starts of motion trajectories. He considers trajectories on the ellipse, and somehow the story is, or the legend, that he found this out in the center of Siberia when Napoleon took him away in custody when he left Moscow, but left a couple of hundreds of thousands of soldiers there in winter 1813, 1814. So this is the idea that he found this theater in the center of Siberia. So going back now, I want to give you an impression of what mathematics educators might be interested in knowing. Perhaps I don't know if I can convince you that this is reasonable, this is not the intention. The intention here is to see a bit more on whether experiments actually help or are even needed by some students to deepen mathematical knowledge. In Germany we have, and I think many other countries too, after the shocking results of the PISA testing, which have shown that while German students did not perform the way the country would like them to perform, a lack of abilities to apply mathematics was observed. At least this is the political consequence of it. And the question is, now we have a lot of shapes of certain tasks which become very important, proclaiming a certain way of how applied mathematics is understood. And it's a bit difficult to link this to mathematical knowledge sometimes, because you have strategies to solve certain problems, but it's difficult to see whether this contributes and how this contributes to deepen mathematical knowledge. So this is a difficult question. And to advance, to go in the direction of understanding this relation better, we tried to give the experiments of the billiards to it, and in the framework of mathematical modeling, we tried to combine this with an idea of how to see how knowledge of mathematics is advanced, to combine them and to see whether we find out how experiments are linked to it. So the framework of modeling is that you have somehow a world of experiments here in this context, and the world of abstraction, of mathematical abstraction. So right is somehow perhaps the content definition of mathematical knowledge. On the left-hand side is the world around us, and it's consensus that it's impossible to remain only in the world of mathematical abstraction to see whether you are able to work mathematically well. I think this is clear, but the question is, how do the both components, so content knowledge and other knowledge, relate to each other? So here, of course, you have experiments. So students can take actions to experiment. And here you have problem-solving situations normally. And then in between, you must see how to build up mathematical models. And if you have and to solve them done, and then here you have the actions, how to interpret the solutions of the problem-solving actions you have in the world of mathematics. This is the classical way of describing the mathematical modeling, which you know probably. So, how do the students construct now knowledge? This is the right-hand side, and we structure this with a so-called nested epistemic action model for abstraction and context. This means we distinguish three things. First, there's something you recognize. So you recognize, you recall what you know. Then you build with something. This means you work with things you know. And then finally, after certain steps and in a long period, you rebuild and create new knowledge, new constructs in your mind. So what we did, we gave here circular billiards to students. And so they really could carry out experiments with the ball. The black thing is made of concrete, so students of mine found out that if you have a lid on that this is sold somewhere for lids on the ground where water goes through, for water channels. So they found it because it's not so easy to build a circular billiard where you can really have reflections for a number of times. And now we gave them 60 minutes in groups of 3 or 4. And first they should use experiments to find paths of the ball returning to the starting point and the boundary after exactly 4 hits. Then they should use dynamical geometry software to simulate the movement of the ball, which returns to the starting points after 8, 9, or 10 hits. So GeoGebra, for instance, we took a different program at the time, but now we're doing GeoGebra. And third, investigate whether every trajectory of a ball returns to the starting point after finally many hits. And then again, assume for this that there's no friction, the ball rolls at constant speed. This is something which is not at all true for the billiard ball they have in their hands. So after 3 or 4 hits, it changes completely if you do this. Now, we did the following. So we carried out the experiments, and now you carry out the experiments, and then you explain mathematically what happens. We look here at the world of experiments and the world of abstractions. And now here in this strange graph, I try to see whether they are in the world of experiments. This is when you have a line from top to down on the left-hand side. On the right-hand side, you have the world of abstractions. And if they are skew, this means that they are in one world, but they provide a link to the other world, you see? So that they try to link these two, but starting either in from this direction or the other. And here you have the timeline. So we look here for the first group at the first 20 minutes. And here the colors, I don't go very much into detail there, but these are these 3 steps of how the knowledge is constructed. When you recognize your knowledge you have, or you build with new one, or you construct something. Now you have experiments, also in 2 colors. One is whether it's really carried out, and the other is whether it's discussed but not carried out, because this is what you discuss on many things you should do experiments with, but sometimes they are not carried out for one reason or another. Now, we start for experimenting. So there's always, we'll also use a kind of heuristically rich period of discussion where you do both. So most of them start with experiments, but this was somehow the task, and then there's some weird situation where they try to get ideas where it's very active. This is something normal you know from problem solving. You have heuristically a certain period where you use your heuristical strategies to approach the problem. Now, here we have students who work in a fashion that I call mathematical approach. because you see that after a while, for them it is just on the right-hand side. So they just take the experiment to define a classical problem-solving task in mathematics. So they have here this situation where they shift from the experiments to the mathematics, and then basically they stay within the mathematics and the experiment doesn't make any difference to them anymore. So they just take it as a definition for things they want to find out. And then here they really find a construction, so in the end they really have proved something or extended their knowledge. You see this here. So they only remain there, and there's only one small instance where they consider an experiment, but all the rest is false. And what you also see that here, you see experiments done at the beginning here, but they hardly discuss on how an experiment should be done. They just do something to get a feel about it, perhaps, but they are not experimenters in the way that they set up an experiment. Now, if you carry on, if they have found something and they go into a new problem, then they go perhaps back to an experiment. Because it's a new problem, it's a new situation, then they go to it, but they quickly, you see here, when you consider the timeline, that they quickly go back to their purely mathematical considerations. Sometimes they use their experiments, if you see this truth, as a language tool, because their mathematics is often not rich enough to explain this, so they rather use the experiment to describe the phenomenon. And this happens normally just when another construction, right or wrong, has been done. Now let's look at the exponential approach. This has a long period first of experiments, and then you see there that it starts and moves from right to left. So they always come back to experiments. Here, 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 and more importantly, in the end, they want to see whether what they considered is really carried out in experiments. The others are not interested about it. They have their problem, and mathematics solve it, and it's done. This type of people wants to see whether what they thought is interesting. So, by and large, we have two different approaches. The mathematical approach and the other. No, this should be the experimental approach. I don't know why it's not there on the right column. So you have a shorter beginning of experiments in the mathematical approach and a long and extended period in the experiment in the other approach. The students create that mathematical task without experiments. So I just make a complete problem-solving situation out of it. And the other students go back to experiments pretty often and also discuss whether they should carry out an experiment and how they should have done it. So the mathematical approach is they only reach it after a certain construction. They are ready to take another experiment, and the others want to have an evidence of their results. Although they discuss also mathematically, I mean both of them were pretty much on the right hand side, but they want to have an evidence later to see what the experiment does to them. So I would like to sum up now what we've done. So I wanted to show billiard system as an example of a task or series of tasks that can be applied from grade 5. They can lead to conjectures and proofs if you intervene as a teacher. They can be done several times in the school career in different geometries and circumstances. So my idea is that, well, it appears over and over again, but not, I don't say that now billiards is everything. It's a task that you can buy now from sooner or later just give in with a certain geometry, different activity than perhaps if they do something with computers. So, and the advantage is that normally once they work with it, they can go quickly back to it without a long phase of introduction in your school classes. the interventions of teachers are necessary, but they are doable because somehow the task is somehow rich, but it's still pretty close because the geometry determines pretty much what happens. So it's not, it appears very often, but since there's the geometry of the table, it's not that open, so it's pretty easy, and if you give something, pretty easy to give ideas how to get to a point, because other open tasks are sometimes so open that it's very difficult to organize a situation which doesn't lead to absolute chaos in the classroom. And then they are paradigmatic for typical mathematical activities. This means that, for instance, the dynamics of describing this with analysis and how you do this is pretty typical for certain mathematical activities. And this is why I think it is, well, I would be happy if some of you, just as a short occasion or so, just have a try to see whether it also works in your classrooms. But of course, it is not meant to limit this to billiard systems, but to, we have done other paradigmatic situations, for instance, the free fall. So I like to use the free fall of, for instance, coconut or something like this to explain, so as a leitmotif in some sense for the differential for analysis at school, because you can apply this in a rich way. Or paper folding is another thing which you can apply in different things for growth, or other ideas you might have. So thank you very much for your attention.